So yeah, watch your language because this is going to be recorded in perpetuity. It'll go on your permanent record. But without further ado, I'm delighted to welcome the National Director of Training for the entire United States of America, Rob Kumpf. And Rob Kumpf is taking over, and he's taking the training program on and really going in a good direction. So Rob, how'd you like to say a few words for us?
Sure. Thanks, Bob, and thanks for inviting me. I'm excited to be here. Before I get going too far, I want to commend Bob Allen here for a second. So Bob Allen was with us down at the N-Train meeting this past weekend or week. I don't know. I was there for way too long, it feels like. But Bob was down there for our meetings, and then he drove all the way back to his house, did a service on Sunday at his church, and now he's here tonight holding this. So I don't know how Bob does it with the energy, because I am still recovering from N-Train for sure. So like Bob said, my name is Rob Kumpf. I'm originally from the 9th Western District. I'm over in Division 31, which is on the far east side of the lake. So we're actually closer to 9 Central than we are most of our shipmates in 9 West. Been in the auxiliary for about 10 years, and I'm super glad to be here tonight. I can tell you from my experience, AUX weather was one of the most challenging courses I did, but it was also by far one of the more interesting courses I've taken in all my time in the auxiliary. So I'm excited to sit through this tonight. As I was poking around tonight on the online stuff, I was having flashbacks to when I took it, and I started looking up other weather stuff, and you know how that starts. You start looking up one thing, you go down the rabbit hole, and next thing you know, you're almost late for the class. So super excited to be here. I think everyone here is going to get a ton out of this. I know I did when I took it. And I thank certainly Bob, Samantha, and the other instructors who are putting this on for doing this. I'm looking around the room right now, and I see people who I know from up here in my AOR to people I have met from all over the country. So this is pretty exciting. We have 56 people on this call from across the auxiliary, which is pretty amazing what we can do with technology. So glad to be here, and can't wait to see what we learn tonight.
Fantastic. Well, welcome. I'm going to take this. All right, one more.
I guess I'll point out one more thing while Bob's getting adjusted there. Samantha, I see you're wearing a Cutterman pin, and I want to point that out to everybody here. Correct me if I'm wrong on this, Samantha, but I believe that there are only 26 people in the auxiliary who actually have qualified for the auxiliary Cutterman pin. So congratulations on getting that, Samantha. And that's awesome. Very rare.
Good. Well, I turned off the noisemaker over here, and we are going to proceed now. If anyone has any questions, I'm going to ask you to go into the chat and send a message to Samantha or Chaz. And welcome everyone. Thank you all for being here. This is a challenging course, and it's an exciting course. And after the big storms we've had in the last few days and the heavy rain in California, there's a lot going on in this country that make weather very interesting. One of the things with the Zoom that I have been told is that there might be bandwidth issues if we leave our cameras on. So I'm going to go ahead and ask you all to go ahead and in the left-hand corner, mute. And Rob is still here. I also was going to ask you, if you know how to use Zoom, on the bottom rail, if you move your mouse around, you can give Rob a big thumbs up for being here. You see in the upper left-hand side of my screen there. So let's all give Rob a thumbs up here, since we can't clap in a normal situation. Thanks for being here, Rob. Fantastic. All right.
Glad to have been here.
I'm going to go ahead and start sharing my screen. So if you all would go ahead and mute your microphones so there's no noise in the background. I'm going to start sharing my screen. And let's talk about weather. Slideshow. Good. And if you do have any...
Hey, Bob, excuse me, Jock Whittlesey here. Occasionally we get this noise that sounds like a vacuum cleaner in the background. I don't know whether that's at your end, but it has come on and off a couple of times. It is on right now. Sorry to interrupt.
Hear a whine in the background? All right, Chaz, do you know how to go through? I'm going to go ahead and make you co-host, Chaz. And if you know how to go through and mute people, Chaz? That also could be my computer, which is a possibility. All right. Sorry about the noise. I thought I got rid of it when I unplugged the fridge, but we'll see how it goes. Well, again, welcome everyone. So let's talk about the weather. How about the weather? One thing is, I studied meteorology at the University of Wisconsin, and I enjoyed it. Thrilling topic. And the one thing about being a meteorologist is that on the TV, if they make a mistake and say it's going to be sunny tomorrow and it rains, nothing bad happens. But I took my degree and went on to be an air traffic controller, whereas if you make mistakes there, for some reason they frown on that. I don't know why. So it would have been much easier for me if I just stayed in meteorology. So no attempts to add or delete information. We're not going to do any of that today. Let's move forward in the slide show. All right. Chapter 1, what drives the weather? I think that we're going to get right into the introductions for this class. All right, this is an overview of the class. AUX weather. We're going to talk in AUX weather about solar radiation, heat and temperature, the relationship between solar energy and weather, how the energy balance works in the atmosphere, temperature and temperature scales, one of the few things where we have to work on math in this first chapter. Specific heat. What is specific heat? We'll talk about that. Types of energy transfer within and between objects, conduction, convection, that kind of thing. Global winds and the Coriolis effect. And which is that's amazing when you determine that how it impacts us. It's not a force, it's just an effect. The global wind and pressure patterns, the impact of the Earth's rotation on the nature of winds, and that gets back kind of that Coriolis topic again. First section of chapter 1 here, introduction to the class. This course is designed to give an auxiliarist, whether you're a pilot, which I am, a coxswain or crew, a basic understanding of meteorology and weather phenomena so they can be safer and more effective in their roles. So this class is very important in that it is for some of our members who are surface folks or may give information, such as using the radio, having a good idea what's happening with the weather is very important. So by necessity, it includes some very simple physical principles, but nothing above high school level. It will not make observers or forecasters of you, but will teach you how to make use of the vast stores of information about current and forecast conditions. Contact my friends at the National Weather Service. They may be joining us for chapter 7, which would be exciting. The focus at the end of the course is on education about weather dangers and how to avoid or overcome them. And did I mention the final exam is open book? All right, course outline, part 1, the science of meteorology. Chapter 1, what causes the weather? 2, talks about pressure and winds. Chapter 3 discusses moisture, latent heat, and stability. And that's a little challenging to understand, but it's really kind of exciting once you get some of the basic principles. Part 2, a wide variety of weather phenomenon. Chaz will be joining us to present chapter 4 to discuss air masses, fronts, and cyclones. Chapter 5, Dan will be here to talk about clouds, precipitation, and optical phenomena. Chapter 6, severe weather. Chaz will share that because he just likes the excitement of it, which is great. Part 3, how do I apply this information? I'm hoping the National Weather Service will share information about observation. And Mike over there will talk about forecast data sources. And our friend Samantha will talk about chapter 8, preparing for and executing a mission. And Samantha, if there's something that you get a chat and something that I need to address right away, let me know and we'll take a break. Otherwise, hopefully Samantha and Chaz can answer all your questions. So we are helping you with this class, but the work will be yours. And when you complete this course, you'll have a sense of achievement because it is interesting, it's challenging. First, be sure to read the text and answer the study questions prior to class. And I'm recording this session right now, which is very helpful. And what I will be able to do is, as I'm recording it, I will be able to save that on my YouTube channel and send you the link so that you can watch it. If there's something in our discussion which wasn't really clear, or if for some reason you miss a class, it's not the end of the world, but I do encourage you, as you saw my emails, you do need to read the material as if you're going to be here on Tuesday nights, 8 Tuesday nights in a row. Those of you that were thinking it was 7 o'clock Eastern time, I'm sorry about that. It's 7 p.m. Chicago time, which is where I'm at. You should read the study guide prior to coming to class. If you are unsure about something in the material, ask the instructor and/or discuss it with your fellow students. And because we're virtual here, that may be a lot easier just to ask me or Samantha or Chaz. Appendices A and B in the back of your student study guide, they have more information that can take your knowledge to the next level. So it's good information, but you're not going to be tested on it. It'll just give you an opportunity to expand your understanding. Finally, approach this course with a sense of adventure and have fun. Some of the members in the last class we taught 2 years ago loved sending me different pictures of fog and other weather phenomenon, which if you send me a photo, expect me to forward it. I'll be passing it out to the rest of the class, just like I did Bill Luxshaw's hail picture, which you should have all gotten a couple days or earlier. What is meteorology? Meteorology is the science of the atmosphere, its physical characteristics and its principles, including weather in all its forms. So it's not studying the big stones that fall out of the sky and from outer space. It talks about atmosphere. Weather is the current state of the atmosphere or its forecast state at a given time or for a given time span and for a given place or a defined area. And we're going to talk about different global and mesoscale, different sizes of areas where we're going to talk about the weather. Finally, climate. Isn't climate the same as weather? No, technically, it is the long-term average of the weather at a given location over a defined area. So the typical time spans are 30 years or more. So we're talking about climate, we're talking about over the long term. Section 2 of chapter 1, we're going to discuss solar radiation, heat, and temperature. An overview of this section, the importance of solar energy, we're going to touch on that. The spectrum, so different forms of heat energy, variation with latitude and the season. And this is a fun thing to talk about, especially if you and I do go down to Florida, enjoy the nice warm temperatures down there, and then fly back here to freezing, snowy Chicago. Also, distribution within the atmosphere of solar energy. Next, the nature of energy and heat, temperature, types of energy, heat as the manifestation of energy, the common temperature scales, the nature and importance of specific heat, and finally, the transfer of energy here in section 2. What is solar radiation? The sun is a large thermonuclear furnace that derives its energy from the fusion of hydrogen. It radiates energy at all wavelengths, with the peak in the visible or green part of the spectrum. It also emits large amounts of energy in the infrared and ultraviolet portions of the spectrum. So for the sun, besides the visible, the ultraviolet energy is important in the energy balance of the upper atmosphere, and we're going to come back to that in chapter 3. So as far as the sun's concerned, only a very small portion of the total solar output that arrives at the Earth has a profound effect on the weather. This is starting to get into a little the technical portion here in terms of what is the solar spectrum. So the sun radiates as though it had an average temperature of 5,250 degrees Celsius. So you can see in our diagram here, and it shows the diagrams here. So the black line shows you the average temperature of the sun. So the yellow area shows the spectrum at the top of the atmosphere. So you notice they get more sun at the top of the atmosphere than we get down here at the surface. So the red spectrum is at sea level after the atmosphere has absorbed and reflected part of the energy. And we're going to talk about the kind of things in the atmosphere that bounce some of that energy back into outer space. So an NM is 1/1000th of a meter. So it's a very small distance. Nanometer, right? And here you could see from this graph that in this wavelength, the 500 nanometer wavelength, the sunlight at the top of the atmosphere is pretty much at the top of the bell curve here. Spectrum radiance there shows up almost 2. But as you get closer down to sea level, here's the black body spectrum right here, the black line here. And what happens with water, it causes it to reflect some of that heat coming at the Earth. And down here shows you what the radiation is like at sea level. So if for some reason we were up there at the top of Mount Everest, it would be a lot sunnier. And of course, it'd be higher in the atmosphere, so it'd be colder. But we'd be more likely to need sunscreen at the higher parts of the atmosphere. We need it now when we're outside in heavy sun anyways, but obviously a lot brighter up there, a lot more radiation. The distribution of solar energy. Radiation that impinges straight down on a surface deposits more energy per unit area than one that impinges at an angle. I use that word impinges there. It's kind of how it hits, right? So down at the equator, where the sun is directly above, it's a lot more intense, right? The sun's energy as it hits the surface of the earth, it's a lot more direct radiation. But as you move north on the planet, on this globe, the solar radiation at the equator is therefore more concentrated than at the poles, because you can see it kind of hits kind of side swipes the planet up here. And so it's not as direct as it is down at the equator. Thank you to USA Today for this picture. So one of the things we're going to talk about is the effect of the seasons. As the Earth spins around, as it rotates around the sun, the Earth's axis tilts by 23.5 degrees. As it revolves around the sun, its axis points in various directions relative to the sun, but always points at Polaris. So, and you notice one of the things from the text, I hope you caught this, is there's a little bit of wobble in it too. So that varies a slight amount. The north and southern hemispheres receive more energy at certain times of the year. So there's more energy being received in the northern hemisphere in June, and the southern hemisphere, December is the middle of their summer. So as someone once said, the seasons in Australia, this is someone from Australia, said the seasons are front to back, because in the middle of our winter, they're getting their summer. So we get roughly the same amounts of energy in March and September. So I think the next slide talks about the seasons have a dramatic impact on the amount of difference between temperatures. That's what affects the difference in temperatures is the seasons. Let's talk about the energy balance in the atmosphere. So you notice from our graph here that some things reflect a substantial amount of solar energy. Right here, if we have very thick clouds, that reflects back into outer space 75 to 95% of the sun's radiation that's coming down to the earth. Another big one here is, let's say you're in up there in Buffalo, where they got a lot of snow this year, or in the upper peninsula of Michigan, or maybe in the mountains there in California. This fresh snow reflects 75 to 95% of the sun's radiation back. So that's going to keep it cooler in those areas. So not all solar energy is absorbed at the surface. Clouds and dust scatter visible light. Bright surfaces reflect more than dark surfaces. So let's say there's some dark trees here. They're not going to reflect a lot of that solar radiation. They're going to capture most of it, 90 to 97% of it, so that only about 3% to 10% of that solar radiation is reflected back into outer space. Water is the same story here. It absorbs most of the sun's radiation, only reflecting about 10% of it back into outer space. So you can see lighter colors here, like lighter colored sand, it's going to be more, maybe up to 45%. A darker green field, only 30%. So, and if you just had thin clouds above you, and you were someplace where there was a lot of sun, just because you got thin clouds above you doesn't mean you don't want to put that sunscreen on, because a lot of that solar radiation is going to get through there, up to half, 30 to 50%. This is a pretty busy graph. So what this is telling you in this graph is, here comes the sun. This talks about the energy balance continue. So you got incoming solar radiation, and it's coming down here, and for a number of 342, that as it comes down, only about 168 of that 342 is absorbed by the surface. How come all of it isn't absorbed by the surface? Well, up here in the upper atmosphere, you'll have a part of it that is reflected by clouds, aerosol, and atmospheric gases. So, and then at the surface. Some of it is reflected by the surface. We talked about lighter colors. And so of that 342, 107 is reflected right back into outer space. Now, how come the Earth doesn't turn into a cinder right away? Well, the Earth later on in the day, as the sun gets lower, starts to radiate that solar radiation back out. And so that here you have thermals, that kicks them up in the atmosphere, surface radiation later in the, during the day as it goes on, radiates a certain amount. And some of that hits off the bottoms of these clouds and will come back at the surface and gets reabsorbed. So you see, it's a pretty some of it gets through. Here's 40 getting through. But as you can see, there's a lot going on here. You don't have to memorize these numbers. You just have to have a good understanding that all solar radiation is not absorbed by the Earth, and some of it is reflected back, and more of it later on is surface radiation that goes back out into outer space. So once absorbed, energy is re-radiated and then sometimes reabsorbed many times over in the infrared portion of the spectrum. It balances at the surface and at the top of the atmosphere. Let's talk about temperature and heat. Temperature is a measure of the average kinetic energy of molecules in an object. This is a definition you want to have a pretty strong understanding of. So temperature tells you how much kinetic energy that molecules have in an object, and it's the average. On the surface of say a boiling pot of water, it may be a little cooler than farther down in that water. So the average is what you're measuring in the temperature. Thermal energy, example calories, is the total kinetic energy of molecules in an object. So thermal energy, which is the total amount of calories of energy that all the molecules have in that object. Heat is the thermal energy being transferred from one object to another. And we're going to talk here in just a moment about how that happens. Heat always flows from the hotter object to the colder one because it has more energy. It just passes it from the hotter object to the colder one. So here you can see how the molecules, they're kind of, bunched up here. So it's cold, it's less kinetic energy. In this example, which is warmer, the molecules are bouncing around. They've got energy, there's more kinetic energy, and so they're farther apart, as they're banging off each other, they spread out. So here's cold, this is like a little pretend thermometer here, and here's hot, and it's all the way up to the maximum. So there's a lot more going on in this situation when those molecules are bouncing off each other. So here's a measure of the kinetic energy. It tells you how much motion, molecular motion, is happening with that object. There's two primary temperature scales. The one that we've used in the States here for many, many years is Fahrenheit. And Fahrenheit is obviously the temperature of fresh water freezes. Not salt water, but fresh water freezes at 32 degrees. And fresh water boils at 212 degrees in standard pressure conditions, which is 1 atmosphere. And the Celsius temperature scale, it starts when when ice melts or fresh water turns into ice at 0 degrees. I think they refer to it later on when they ask you some questions. This is the temperature at which ice melts at 0 degrees. And obviously the same temperature where if it's below there, it freezes again. 100 degrees in Celsius is what you can cook in if you're making dinner. It's 100 degrees. That's when the water is going to start boiling at standard atmosphere. This is something that you do want to kind of commit to memory. Now there's the green one is kind of a shorthand way of doing it, but here is converting Fahrenheit and Celsius. In this case, if you start out with Fahrenheit, what that equals to is the Celsius temperature times 9/5 plus 32. So a down and dirty way to do it, just a real quick, have it in the back of your mind. Basically, this number is going to be the Celsius temperature. Well, let's say the temperature is 20 times 2 minus 10%. Let's say the Celsius temperature is 20. So 20 times 2 is 40 minus 10%. So it'd be 40 minus 4, right? 10% of 40 is 4. So that's 36. And then you add it to 32. So 36 plus 32, that's 68. So if your temperature in Celsius was 20, the Fahrenheit temperature would be 68, roughly, right? Pretty good. So let's say we needed to convert from Celsius into, or we wanted to take Fahrenheit and turn it into Celsius. So let's work the problem backwards. It works pretty close there too. So you got 68 degrees Fahrenheit minus 32, which is 36. So then we have to multiply it by 5/9, and it's going to be very close to 20. It's going to be slightly different because the fractions don't work out perfect. But this, if you wanted to do it quick and dirty, and you're trying to figure out what temperature Celsius is it, you can take Fahrenheit temperature, which we said was 68, minus 32, which would give us 36, plus 10%, which is close to 4, a little less than 4, divided by 2. So it is 40 divided by 2, which give us 20 degrees Celsius. So that just kind of gives you a rough way to remember that. But this calculation, especially the shorthand, is going to be pretty necessary for you to have a good idea about. So look that over a couple times, write it down if you need to. And some of the review questions that you'll get later on will really help you figure that out quickly. What is specific heat? Specific heat is defined as the energy it takes to raise a fixed amount of substance by a fixed number of degrees. You want to warm something a specific amount. The units normally used in meteorology are calories per gram per degree Celsius. This calorie is the gram calorie. A lot of times you see this abbreviation, CAL. For measuring food energy, the kilogram calorie is used. So it's 1,000 times larger than the calories we're going to talk about in specific heat. So the calorie is defined by the specific heat of water, the amount of energy it takes to raise 1 gram of water 1 degree Celsius. So this definition is kind of handy to remember. How much specific heat does something have? It is defined as the amount of energy it takes to raise 1 little bitty gram of water by 1 degree of Celsius temperature wise. The specific heats of soil, vegetation, etc. are lower than water, so they heat and cool faster. That's going to come up a lot. Soil gets hot faster than water does. So soil, vegetation, or etc. are lower than water, so they heat and cool faster. And then we're going to talk about that again in chapter 3. There are 3 common methods to transfer heat energy from one object to another, or from one part of an object to another. This is also a good thing to pay attention to because it helps you understand. There's a nice graphic in the next slide. Conduction. If you have molecular motion, it's transferred from one molecule to another. It occurs in solids and liquids, but very little in gases. So here, conduction is like you put your hand on the stove. Now that heat is going right onto your hand. Convection, the physical movement of parts of the substance, usually vertically, and that word vertically with convection is going to come up a lot, as in heated water, also occurs in gases. So there's a boiling pot of water on the stove. You don't put your hand in the boiling pot, but you hold it above there, and the convection comes up and makes your hand very warm. So in meteorology, horizontal movement is also called advection, which is side to side. So this is, we'll talk about that more later. What about a way of transferring energy called radiation? Radiation, the remote transfer of energy by electromagnetic radiation. It does not require a medium for transfer. It is actually more efficient in a total vacuum. So this is where you you're going through the airport and you have to go through the screening by TSA, and somehow they're able to see right through your shirt in case you forgot and left your wallet in your pocket. And they use radiation. It goes right through there. It doesn't need a medium for transfer. So examples of each of these are on the next slide. Let's check that out. So here you got, let's say you put a piece of metal. It's not your hand we're worried about here. It's the piece of metal. So if you put that piece of metal right in the flame, that's going to conduct the heat. The metal itself will become warm, and eventually your hand might get more warm too. But you put it right in the heat there. Convection, you've got boiling pot of water on the stove. You're heating the bottom of the pot, but that's causing the heat inside here to rise to the top of the pot. So we're not talking about the temperature energy transfer at the bottom of the pot. We're talking how does it get hot at the top of the pot? And that's because that the warm temperature rises up through the surface. And finally, radiation. You don't actually have to be touching it, but if you're in the room and not too far away from the stove, the heat generated, or the heat generated by the burning of these fossil fuels, you'll feel it, even though you're not touching it and you're not directly above it. All right, let's talk a little bit about the station model if you are going to look at a weather map. So how can you figure out what the temperature is? And what happens is it talks piece by piece about the different things that you'll see on a weather map. And the first thing they're going to talk to you about is the most obvious one. Weather measurements are plotted on specific charts in a specific way. So for us here in the States, temperatures are going to show up as Fahrenheit, not Celsius. So when we look at in America, if we look at a weather map, they're going to tell you what the temperature is going to be in Fahrenheit, not Celsius tomorrow. Shown here is the station, someplace not too far away from you. That station is represented by a circle, and the temperature next to it is in Fahrenheit. So this is 67 degrees Fahrenheit. So as we go through the class, we're going to add a few more pieces of information to these station models. And then when you look at a weather map, you'll have a pretty good idea what you're looking at. Finally, in this chapter, section 3, global circulation and the Coriolis effect. And this is pretty exciting for most people once they see this. The Coriolis effect, what it is and what it is not, how it affects winds, and it's different in the northern hemisphere as compared to the southern hemisphere. We're going to talk about global circulation, and you hear about this sometimes, about cold air coming down from Canada, or warm, moist air coming up from the Gulf of Mexico into the center part of the country, or the Chinook winds out west. Global circulation. Without Coriolis, what would it look like? Then we got to talk about how our world is with Coriolis as that Earth spins. Finally, pressure bands, the prevailing winds, and that's something that we're going to talk about a lot, and the effects of oceans and continents. What is the Coriolis effect? So it's a term added to equations of motion when converted from a fixed inertial to a rotating reference frame. In our case, that frame is the Earth. The Earth isn't standing still, it's spinning around like a top. The Coriolis effect has several properties. It causes winds to curve to the right in the northern hemisphere. And that's something you're going to need to, we're going to bring this up over and over again. Coriolis in the northern hemisphere causes the winds to turn to the right. In the southern hemisphere, it causes winds to curve to the left. So front to back again, down in Australia, it's a little wild and crazy down there. Their winds are curving to the left because they're south of the equator. It increases with increasing latitude. So at the equator, there's no Coriolis effect. At the North Pole or the South Pole, it's at its maximum. So the stronger the wind, the stronger the Coriolis effect. It increases with increasing wind speed, and it is effective only over long distances. I don't know why they have to share this, that your sink doesn't count as a long distance. Although it is not a true force, it behaves like one, so it does impact our weather. And the next slide shows a very simplistic image to tell you why it exists on our planet. Let's say you had your latest Engelbert Humperdinck record. I know you're all big Engelbert Humperdinck fans, and you put it on your your turntable there in the house, which those of you, some young people, there's a thing we used to call a turntable. Actually, they said last year vinyl outsold downloads, so maybe everybody has a turntable now. So here you've got a disc, and it's not sitting there, it's rotating. So you're looking down on the Earth from up above, and the disc is rotating like the Earth viewed from above the North Pole. And let's say you wanted to draw a line from the top to the equator, top to the bottom. Well, what happens is, as that Engelbert, your favorite Engelbert Humperdinck song is playing, or is it Neil Sedaka? Who knows? Or Neil Diamond. It's spinning here. And as you try to draw a straight line from the top to the bottom, the disc is moving. It's not standing still. So you start at the top and you try to go straight down, but as you're moving your finger down here, it ends up looking like a curve, because underneath your hand, that 78 or 45 or LP 33 1/3 is spinning around. So here you can see when we're all done trying to draw a straight line, hopefully he doesn't get arrested by the police for being drunk, because he didn't draw a very straight line, did he? What ends up happening is the line becomes a curve, and that is the essence of the Coriolis effect. If you could see the wind from outer space, it follows a straight line. So pretend this is a vector of the wind. It goes straight south, but as it tries to go south, underneath it, the Earth underneath the wind is rotating. So it ends up looking like the wind is turning to the right. And that's going to come up over and over again. If you see the wind from space, it follows a straight line like your pen. But if you watch it from Earth, it curves like a line on the cardboard. You notice here, this reinforces this note. Winds in the northern hemisphere will appear to curve to the right. And well, they do curve to the right as the Earth rotates. But if you're down in Australia, Melbourne or Sydney or someplace like that, winds in the southern hemisphere appear to curve to their left, or maybe down in South America. So the disc is rotating. We talked about that. So if a person draws what appears to be a straight line, like you're throwing a ball in outer space. But if you're on the Earth, an observer on the disc, as the disc is spinning around, we'll see the line curving. That's kind of a hard one to understand at first, but it's fascinating. Global circulation on a non-rotating Earth. All right, what if the Earth didn't rotate around? Well, on Earth, it doesn't rotate. You have the hottest point on Earth where most of the solar radiation would be absorbed, would be down here at the equator. So at the equator, this gets hotter quicker, so the air here rises. And as it rises here, it needs to be replaced by other air. So it draws air back towards the equator here. And that air is coming from the North Pole, because as the air goes farther north on the globe, it's getting into a cooler area and it sinks in this non-rotating Earth. This is a science project here. And then once it sinks at the North Pole, it has to rush back and fill the empty spot that the other air made when it rose down here. So this is a circulation model in our imaginary non-rotating world. Here, the winds at the surface would always be coming from the north. Up at high altitude, the winds would always be coming from the south in this circular global circulation in our imaginary world. So in this scenario, we would call circulation like this a Hadley sail. So the Earth is spinning though. Sorry, Mr. Hadley, the Earth is not sitting still. So as it's spinning, things are going to start changing. We got different things that are going to change. Now, global circulation with the real Earth, the rotating Earth, with the Coriolis effect, a single Hadley cell would not be stable. And it would have to break into 3 cells, because the Earth is spinning around and there's only so much space, or volume of air there. So it has to go someplace else. So here in the lower part of the globe, closer towards the equator, I should say lower part, I should just say closer to the equator, you could still have our little Hadley cell, but as it gets farther north, the impact of the Coriolis is much greater, right? The Coriolis effect. And so things are going to be rotating the right around there. So the lower part of the latitudes closer towards the equator here, you could have a Hadley cell. But as you get up here, before it gets up here, other circulation is happening in the center of the atmosphere, and there's something called a Ferrel cell, which is halfway between the polar cell and the Hadley cell. So where the air rises, the surface pressure is low. So down here, the air is rising. That means that surface pressure here down is going to be low, which is going to cause other air to go in that direction because it wants to fill the hole made by, or fill the empty space made by that rising air. Where air falls, the surface pressure is going to be high. So here, as the air starts to sink back, it's not as hot here as it was down in the equator. So this air starts to cool and down she goes like an elevator. Well, that's going to push more pressure on the earth and create what we would call higher pressure from the sinking air as the air sinks. And the air is going to want to get away from there because there's more air than there is, there's more pressure than there is in other places. So it'll be pushing in this direction, like your luggage at the airport on the conveyor belt. It's going to push the next one out of the way. Coriolis also affects the direction of the winds. So how does that work? Here's a cross section with different jet streams. Now, again, this is, sort of a scientific chart. There are times when the polar jet and the subtropical jet intersect. But for the purposes of our global circulation, here you've got the North Pole up here. You got Santa up here in his little house and Elzo working on building toys. So up here at the North Pole, the air is sinking because it's cold here. And the air is warmer down here. It's going to push up here until it starts sinking. So closer towards the North Pole, you have this polar cell. And right over the North Pole, the pressure is going to be high as the air is pushing down, as it is sinking. And then it's going to drift away from this high pressure area because in this area here, the air is rising. And so as a result, there'll be a circulation here. So around 60 degrees north, there'll be an area here called the polar jet. And further south, closer towards the mid latitudes, most people in the US live more in this part area and down 30 degrees north area. You'll have another circulation going on, which seems to be spinning in the opposite direction of the polar cell, and this will be the Ferrel cell. And as it does, blowing across the top of it between the polar cell and the Ferrel cell will be a jet stream, what they call a polar jet. Now here it's just conveniently perfectly at 60 degrees north, but as you see from weather maps, it goes up and down. And further south of the Midwest, you get into about 30 degrees north. Here you're going to have that sinking air from the Ferrel cell causing some high pressure down here. And then you've got the equator down here and the air rises in this area near the intertropical convergence zone where it's raining all the time, just like on that movie Romance in the Stone, it's always raining down there. So here you're going to have a lot of weather, and as the air rises, it's going to cause low pressure at the surface. So that's going to create some convection here. And it's going to drift back towards the north because it's warm here and it's cooler up here, and then sink back down again once it gets away from the equator. And you're going to have a second jet stream known as the subtropical jet. So at the North Pole, high pressure. Where the air is rising at about 60 degrees north, a general area of low pressure. And that's going to vary. We're going to show on our maps how that's going to vary in location. So for most of the US, the winds are coming out of the west, what we call the prevailing westerlies. You get further south of there, you'll have the subtropical high. And in this area, you get your trade winds, which are blowing out of the east in the opposite direction. So you got your polar easterlies, you got your prevailing westerlies, and down here, you've got your trade winds, which also blow out of the east. So, and down here's the equator where it's very warm. So if you look at our pressure bands, once we have all the pieces in place here, we got the sun getting the center part of the earth, the equator is very hot, not as much sun being absorbed in this, not as much radiation being absorbed up here. Then you've got the Coriolis effect, and you've got the jet streams as they blow. It's going to have high pressure at the North Pole. Just south of the North Pole, you're going to have an area of lower pressure where that area is rising as it meets this circulation, the Ferrel area here. And then south of there, you're going to have high pressure again, where the hot air from the equator is going to get around 60 degrees, about 30 degrees north and start sinking. So further south, it's the horse latitudes. Right at the equator, they have the doldrums. And those of you who don't know, doldrums means it's not as windy, because as you can see, it doesn't tend to have a consistent direction. So you can, if you're in a sailboat, you're not going to be moving very fast down here in the doldrums because not a lot of wind. And that whole scenario is reversed for the South Pole, except for instead of turning the wind to the right, it's going to turn the wind to the left. So down here, there's this high pressure area just south of the equator where the air is sinking back again. And those are the horse latitudes. And Chaz, you probably better telling the story about the horse latitudes, but they had, we'll talk about that in Chaz's chapter. And then further south of there, as you get close to the South Pole, you're going to have another subpolar area of low pressure. So you're going to see this again. Areas of low pressure are at the equator and up here close to the subpolar lows. You're going to see that again. What are prevailing winds? Well, in discussion with those three different cells and the resulting pressure bands, it causes the winds on the surface to go in a certain direction. The Coriolis effect will bend the winds so they don't end up going straight line all the time. But as you can see here from our map, at the North Pole, you have easterly winds just south of the North Pole. We discussed the prevailing westerlies that impact a lot of the US. And once again, as you get down closer towards the equator, not at the equator, but closer towards the equator, you have your northeast trade winds. So in the old days when there was cruising ships that go over to Europe, they would take advantage of the prevailing westerlies, get to Europe, go down here to the Straits of Gibraltar and go south from there, and they could take advantage of their sails, and they didn't need propellers as much. Finally, you talk about the equator where there's not as much wind, but the space in that area moves up and down. We're going to see on the next slide. So the Coriolis effect bends the winds to the right in the northern hemisphere, to the left in the southern hemisphere. The prevailing winds are the trade winds, the prevailing westerlies, like across most of the US, and the polar easterlies. And you notice 2 out of 3 of them are blowing from the east, but the ones we worry about here in the center part of in the United States are the ones that come out of the west. So looking a little bit more at our global circulation, we talked about the polar high, the polar front, which as we know comes up and down. It expands in winter and contracts in summer. The horse latitudes down here, which can have an area where there's not as much wind. And then you get down into the trades where the winds are blowing out of the east. And of course, they're turning to the right, which they do in the northern hemisphere, right? Then you get down into the oceans and there are land and sea surface impacts. This talks about the doldrums where there's not as much wind. And it's reversed in the southern hemisphere. Your southeast trade winds, which are also blowing out of the east. Your mid-latitude between 30 and 60, where the winds are coming out of the west. And again, the South Pole, near the South Pole, winds are easterly. So to summarize, was that enough? Was that enough science for you? I hope you haven't fallen out of your chairs with that. But summary of global circulation from the equator to the poles. The pressure bands are equatorial low, which is right at the equator, also called the doldrums because the winds there are very light. The mid-latitude highs, also called the horse latitudes. So the winds are light there. And then you get the subpolar low pressure areas, subpolar lows, and the polar right over the top and the bottom of the planet are the polar highs. Helpful to remember the next little bit here. The winds are northeast and southeast in the trade wind bands and the trade winds. So notice they both have easterly components. When you get to the center part of the mid latitudes, now you're talking prevailing westerlies. And finally, all the way up close to the poles, you'll have easterly winds there. So it's a simple enough picture until you add land and sea impacts. So that gets more complicated. So the continents, in some areas, because land absorbs heat and radiates it more quickly than water, there's variations in the continents and the oceans. So here in the middle of January, our situation on the Earth is the Asian highlands have high pressure, so rotating clockwise here like a clock. However, close to, in January, coldest part of the year, up close to Alaska, it is rotating counterclockwise or a low pressure area. And by the same token, around Iceland, it's going in a great big circle around Greenland there. It calls it the Icelandic low, but really the main feature is Greenland up here, and which is circling around counterclockwise. But down here closer towards the center part of the Atlantic, you get a high pressure. So it's turning like this. And in the middle of January, you have clockwise south over Hawaii there, which is why it's nice and sunny down there, because it's high pressure. So this is a subject here, the position of the intertropical convergent zone. We're going to talk a little bit more about convergence at the surface later on. But what that zone is areas where two air masses are coming together, and when they smack into each other, the air rises. And if you have an area of rising air, that's going to be rain. So when you hear about the intertropical convergence zone, if you follow this red line right here, you notice it isn't perfectly at the equator because of the impact of the oceans and the land masses. So it's kind of zigzaggy, isn't it? But in this area, right in this area, it's going to be raining. It's going to be raining a lot. So, and then it shows a little bit in January what the southern hemisphere looks like. You got Australia that's got a low pressure over the western part of it. Am I going backwards on it? So I'm sorry, it has a high pressure, but here because of the way the Coriolis is, it turns to the left instead of the right. So I said high, but it's actually a low, but it's actually a high. So it's nice and sunny down there in Australia, which is why it's mostly desert down there. This part of the planet, you've got another low, which is a little confusing because it's a little bit in the southern hemisphere, northern hemisphere. West of South America, you've got another area of high pressure where the rotation around this area will be clockwise. And over Africa, south of there is clockwise rotation. So it's another high pressure. So, but in July, come July, the situation reverses. Here in Asia, you've got counterclockwise circulation. So that's a low pressure area. Instead of a great big Aleutian low, you have high pressure over the Pacific in July, which means less rain for that part of the ocean. And you notice how much further north the intertropical convergence zone is come July. That means a lot more rain for Asia and Japan. And in the middle of summer, you notice you've got the Bermuda high here. It's close to Africa, but during summer, it kind of drifts to the west. And with that high pressure, it's going to be nice and sunny down in this area. And it's expanded, so it's a larger circulation. So you notice here's the intertropical convergence zone in January. It's pretty close to the equator. Well, come July, that intertropical convergence zone drifts to the north of the equator. That means a lot more rain in Africa, a lot more possibilities of rain for this part of the world, the Mideast. And still stays dry here in Australia, which again, why it's a desert. Southern part of Africa also impacted by in this case, it's high pressure, so it goes in the other direction, right? So it is, I've got the back, it goes, the wind turns to the left. Good. Scales of weather phenomena. A global scale or planetary scale is measured in weeks to years. And so it's also a large distance, so 2,500 to 25,000 kilometers. In this case, you have trade winds and the prevailing westerlies, and as I showed you that red line on our map, the intertropical convergence zone. You get to a smaller scale, the synoptic scale, which you'll see a lot on your nationwide weather maps on the Weather Channel, talking about what scale is that? Well, it's less time. So instead of weeks to years, it's days to weeks, and it's 250 to 2,500 kilometers. And in this case, the synoptic scale, which we usually talk about in weather forecasting, deals with different types of air masses or frontal systems, cold fronts, warm fronts, and the high and low pressure areas. We're going to talk more about that in chapters 2 and 4. Get into a smaller scale than that, mesoscale weather phenomena, they're going to be measured more in minutes to days, so a lot less time, 25 to 250 kilometers. So here we're going to talk about thunderstorms, tornadoes, or the impact of sea breezes. We're going to talk about that in chapters 4 and 6. And finally, the smallest scale, microscale, is like a downburst, seconds to minutes, 2.5 to 25 kilometers, so not very much. And in this area, we're going to talk about microbursts, wind gusts, and dust devils. How are we doing out there? Finally, the first part of our summary. Meteorology is the scientific study of the atmosphere. Weather is the current or forecast state of the atmosphere. Climate is the average of the weather over a long period. So remember, it's a longer period. The sun is the source of all energy that drives our weather patterns. More solar energy falls on the equator than on the poles. That's going to come up over and over again. The impact of the axial tilt in the Earth's orbit drives the different seasonal changes. The energy balance of the Earth is complex and ever-changing. And so different impacts we can have from heating or from a lot of snow it's changing all the time. Finally, the sun's energy is strongest in the visible portion of the spectrum. The Earth's is strongest in the infrared. So that release of radiation from the Earth may not be visible. It's going out as infrared energy. Temperature is due to the average kinetic energy of the atoms. The main temperature scales, which we touched on just as a review here, Fahrenheit and Celsius, where pure ice, that's not salt water, pure ice melts at 30 degrees Fahrenheit or 0 degrees Celsius. At standard pressure, pure water boils at 212 degrees Fahrenheit or 100 degrees Celsius. Specific heat is the energy required to raise the temperature of 1 gram of a substance by 1 degree Celsius. A calorie is defined as the specific heat of pure water. Heat energy is transported by conduction, convection, and radiation. We're going to talk a lot about that. In meteorology, the horizontal transport, or side to side along the horizon, is an analog of convection called advection. So we're going to talk about that too. Finally, our last page of the summary, global circulation is driven by unequal heating between the equator and the poles and is modified by the Coriolis effect. A lot of times in this book, they talk about the right turning tendency. They don't talk about the left turning tendency because this class was designed for the United States. The Coriolis effect is due to the Earth's rotation and acts like a force, but it is not one. It increases with increasing wind speed and increasing latitude and operates only over long distances. So the further north you get, closer towards the North Pole, that's when there's more Coriolis effect. From the equator to the poles, the pressure belts are the doldrums, which is low pressure, horse latitudes, which is high pressure, subpolar lows, and polar highs. Land and oceans break these into semi-permanent highs and lows, as we saw from that last model. The wind belts are the trade winds, which are easterly, prevailing westerlies, and the polar easterlies. All right, I'm going to ask questions here, and I know how to go through my questions here. Jock, you want to take a shot at this one? How does the amount of energy per unit area that arrives at the top of the atmosphere change with latitude? You don't have to be real specific, just general terms, Jock.
I would say in general, it's going to drop off because when the energy impinges on the Earth at the equator, it hits it full on, whereas up in the northern latitudes, the same amount of incoming energy is covering a larger area as the surface of the Earth bends away, so ends up being less.
Excellent. Dave Watkins, the largest temperature swings are caused by what weather phenomena? What changes the temperatures a lot? You there, Dave?
Yeah, I'm here. I was gonna say, the Coriolis effect, to be honest with you.
They're looking for something else here, and this really isn't well. What they're looking for is what makes a bigger change in the temperature, and that would be, you know, from winter to summer. So the different seasons. But this isn't a very well worded question. Jean Velez, how about this question? With the same heat input, do the oceans or land heat faster? That's a good question. You there, Jean Velez? You want to unmute yourself? Must be busy. John Tonetti, what do you think?
I would say that the land heats faster.
Right on. Gene, let's have you take the next one. If you unmute yourself, can you give us a general idea of what the specific heat of a substance is? How do we figure out what we're talking about with specific heat?
The rate of temperature that increases for a given input.
Right on, perfect. Well done. Johanna, temperature is defined as? Joanna Wood, sorry, Joanna. I'll take a crack at that one.
It's the measure of kinetic energy of molecules.
Right on, well done. John M. Zills, the temperature of 0 degrees Celsius is? What happens at 0 degrees Celsius?
Pure water melts.
Absolutely. Or melts or freezes. Good job. How are we here? Oliver, how about the transfer of heat by the horizontal movement of air is known as? I missed it. Go ahead. Yeah, I think you got it right.
Advection.
Well done. Bill Madison, the transfer of heat between bodies that are not in contact is?
Convection. No, conduction.
They're not. No, they're not in contact.
Radiation.
Radiation. Well done. Jack Benton, the vertical movement of air is called?
Convection. Oh, sorry.
All right, yeah, don't jump in. I want Jack to get a chance. Yeah, you're correct. It is convection. Jack, how about the next one? No helping. Winds near the equator are called? You there, Jack? How about Anthony? Anthony P. What are the winds near the equator called?
I believe they are the doldrums.
Looking for horse latitudes. No, trade winds. Good.
Oh, trade winds, okay.
Who else? The region of low pressure near the equator, Dave Murphy, is called?
Oh, the trade winds.
Region of low pressure near the equator. I think we're looking for Phil. Yeah, the doldrum. Pat Mussman, the intertropical convergence zone, ITCZ, is located? You there, Pat? I'm not hearing you too good.
Yeah, I'm here.
You want to pass? I'll have Fritz take a shot. Fritz, what do you think the intertropical convergence zone, where is it located? You have to unmute Fritz.
Yeah. Go ahead. Someone else answer because my answer is going to be a guess.
It's on either side of the equator.
Right by the equator. Well played. Fritz, how about this one? Heat is transported north and south from the equator by?
What is that? The Coriolis effect?
Talk about something different. Probably pressure change, right? Yeah, winds and ocean currents, yeah. Catherine Nixon, the region of relatively high pressure near 30 degrees latitude is known as the. There, Kathy?
I'm here. I'm thinking.
It's fun to put people on the spot, isn't it? I'm kind of on the spot too here because I didn't get the words right there, but go ahead, Kathy.
Okay, hold on. Tropics. The tropics? Hold on. The region. Oh,
See who else we can pick. Who else can we pick? Pam, you want to take a shot at this one?
I knew you were going to ask me because it's the one that I'm sitting here going, wait a minute. Horse latitudes.
What's that?
Horse latitude. Horse latitudes.
Over. Well done. Robert Chima, how does the Coriolis effect vary with latitude? You there, Robert? You got to unmute yourself. Robert Chima.
Increases as you go south.
As you get closer to the what?
Equator.
No.
Increases as you get where?
As you get closer to the equator.
No, just the opposite. As you get closer to the poles, right?
Okay, thank you.
As you get higher, yeah. No, this is a tricky one. That's cool though. All right. Let's see. Any questions? Chapter 2, the next chapter is going to talk about pressure and winds. So as having yourself called on, we're going to talk about the veering winds, good times, clockwise. Veering wind is clockwise. All right, we are going to go ahead and look at the questions in your review. And because there's so many of us, I get to keep passing it around. See, Richard Clement, did we have any luck with that? Number 1, the electromagnetic energy that comes from the sun consists of. You there, Richard C?
All of the above.
All the above, right on. Mike P, number 2, the amount of energy per unit area that arrives at the top of the atmosphere from the sun.
Decreases with increasing latitude.
Absolutely. There's another Mike P. All right, Mike Patina, you're going to get number 3. The largest swings of hot and cold are.
What was the letter on that last one?
Oh, that last one was D. Sorry, last one was D.
D dog. Okay, thank you.
And Mike Patina, the largest swings of hot and cold are.
With the seasons?
With the seasons, absolutely correct. Monique, number 4. With the same heat input, which heats faster?
Land.
Correct. Mark B, number 5, the amount of solar energy that is absorbed by the surface is reduced due to.
Is that me, Mark Bagley?
Yes, sir.
Okay, you said Mark B. The amount of solar energy absorbed, it's reduced because of the reflection from clouds and what kind of surface is underneath it. So I'm going to say both B and C.
Right on. Very good. I just abbreviated your last name, Mark B. Sorry about that.
Oh, no worries.
Mike McGann, number 6, the specific heat of a substance is. You there, Michael? Mike McGann?
Oh, Bob? Yeah, I'm sorry. Okay, that's delta. The rate of temperature increases for a given energy input. Thank you.
Absolutely correct. It's just starting to rain here. Michelle, how about number 7? The air in the lower troposphere is heated mainly by.
D.
D is correct. Conduction and convection from the Earth's surface. Travis, temperature may be defined as.
Oh, sorry, I had to go on to mute there. C.
C is correct. Bob Wokey, I know you've done this class already, but we'll ask you again. Number 9, in the Celsius temperature scale, 0 is defined as.
That would be C, the melting point for pure water ice.
Correct. John Puskar, number 10, 20 degrees Celsius in Fahrenheit to the nearest degree is.
You say John Ruse?
Oh, that was for John Puskar. I'm coming for you, John Ruse. You there, Sergeant Major? John P? Might be having trouble with his
Nope. Can you hear me now?
I can hear you, sir. How about number 10?
Okay, number 10, be Charlie, 68 degrees Fahrenheit.
C is correct. Well done. Jock, how about number 11? 59 degrees Fahrenheit is in Celsius to the nearest degree.
15 degrees Celsius.
Number B is correct. Well
No.
done.
Okay,
Oh,
thank
that
you,
was
whoever
somebody
that
else.
was. Yep.
All right, Jock, I'll give you the next one. Jock, number 12. The transfer of heat by the horizontal movement of air is
Advection.
advection. Good. No helping over there. I'm watching you guys. No helping, Bob. Steve Boyer, how about number 13? The transfer of heat between bodies that are not in contact is?
That would be Charlie, radiation.
Radiation is correct. 14, Chris McNamara, in meteorology, convection means?
D, the vertical transport of heat by air.
Excellent. Derek S., number 15, radiation is energy transfer. D is in Derek Steinhoff.
15 is D, in wave form without necessity of a medium.
Excellent. Thomas K., number 16, large land masses as opposed to the oceans.
C, change in temperature more between night and day.
Excellent. Number 17, Dave Bobos, the cause of most weather phenomena is?
D, uneven heating of Earth's surface.
Excellent. Amy, number 18, for the station model shown below, the temperature reported is? You there, Amy?
Hear me? Can you hear me?
Yes, ma'am. Go ahead.
C, 53 degrees.
Good. You got to recognize that they're looking for Fahrenheit in the US. Good. Addison Chapman, number 19, the Coriolis effect.
The Coriolis effect is B, it increases with increasing wind speed.
Excellent. Here. Bob Mack, number 21, on a rotating smooth earth, the low pressure bands parallel to the equator are the blank and the blank.
Letter C, doldrums and subpolar lows.
Correct. Jay Zimmerman, 22, the doldrums is a belt of relatively.
Did we do 20?
Uh-oh, did I skip one?
Yeah.
All right. Thomas Cantus, number 20, the winds near the equator are called.
Trade winds.
Was that? Let Thomas answer.
A, trade winds.
Trade winds is correct. Jay Zimmerman, your first name is John, isn't it? How about 22? The doldrums is a belt of relatively. You there, Mr. Zimmerman in Fairview? Joseph Thalheimer, number 22. The doldrums is a belt of relatively.
C, low pressure.
Low pressure, good. Eugene, number 23. Which of the following is not one of the primary wind belts?
Polar westerly.
Right. Polar winds are out of the east, right? Don Osiniak,
Yes.
number.
I'm sorry, Bob. What was 21 then? I didn't hear.
No
it when
worries.
we missed
20, I threw you off there. Sorry about that. 21 was C, the doldrums and the subpolar low. Danny Mullen, how about number 24? The intertropical convergence zone is located.
D, either side of the equator, depending on the season.
Excellent. Michael Kowal, 25, the trade winds. Michael K, number 25. You there, Mike Kowal? Bill Luckshaw, I'm going to have you hop in. 25, the trade winds. You there, Bill?
Bill who?
Bill Luckshaw.
I'm sorry.
I'll take it.
Go ahead.
Flow from the Horus latitudes to the doldrums.
Good. You're going to see that again. So remember that one. John Cobb, I'm not sure if I called any yet. Vertical motion of air near the equator is caused by. You there, John C? Sharon, what's that, John C? John C.
John Zolls.
No, looking for the other John. Are you there, John Cobb? Can you hear me? He had some trouble plugging in at first. John Zills, go ahead, give us the answer. What number are we on again?
26.
26.
Go ahead, John
26.
Z. Yeah, go ahead, John.
Vertical motion of air near the equator is caused by convergence of the trade winds, heating of the air by the Earth's surface, variation of solar energy with latitude.
So it's all of the above.
It's all the above.
Right on. Sharanda, I don't know if you can answer on your iPhone. 27. Heat is transported northward and southward from the equator by.
I am so sorry. I'm trying to get the kids to sleep.
Oh, sorry, Sharanda.
I'm just listening. I'm so sorry.
That's all right. We'll bug somebody else.
A and B.
Yep. Winds and ocean currents.
Yeah, both A and B. So it's D. All right, coming back around, Kathy Nixon, our number 28. Insulation is?
Charlie, the amount of energy reaching the Earth's surface.
Excellent. Warren, how about 29? An example of a synoptic scale phenomenon is?
Sorry, I stopped after 28.
Oh, yeah. Yeah, did you see my email about it's kind of goofy and that it's all the way in the back of the...
No, I just got lazy after 28.
Air mass. Dave
Which
McCollum,
I missed.
you want to take a shot at that one? Are we at 29 now? What one are we at? I'm confused here.
29.
29.
Dave McCollum, you want to take a shot at 29? An example.
Air mass.
Look at that. Example of a synoptic scale phenomena is?
B and air mass.
Air mass. Excellent. Oliver, number 30, an example of a mesoscale phenomenon is?
That would be a
thunderstorm.
Excellent. Finally, Bill Madison, number 31. The trade winds are an example of?
A.
A is correct. All right. Any other slides you guys want to see again before I shut these off? All right, I'm going to stop sharing if I can figure out how to do that. Stop sharing. All right. Any questions? I'm going to be back on a Tuesday, a week from today. A lot of questions. If you want to turn your cameras on, you can.
We had one question that came up. How are we going to be able to do the final exam? Is it going to be on the National Test Center site?
Excellent question. Yes, the final exam for this class is available on the National Testing Center website. And I'm going to talk a little bit about that later. Did anyone have any questions about how to log onto Auxiliary Classroom? We've still got Rob here, and we could probably beg him for a brief explanation, or maybe everybody's figured it out already. We had a couple people that did not have passwords have sent me emails and struggled a little bit. Is anybody here having trouble logging on? If not, if you are, you can just stay for a couple minutes and maybe Rob can answer that question. Is anybody here having trouble with that?
Yeah, I'll stick around. Bob, Mike,
Yes,
here. I'll stick around. It's been a while since I did it.
Okay, good.
For the NTC you're talking about, right?
Good. You know what? I can share my screen. Or did you want to share your screen, Rob, and show them how you log on to NTC?
Sure. Hang in one second.
Go ahead and jump in, Rob.
Let me get it up here and then I'll share it.
Probably should have given you a little warning. I was going to drop
It's
it.
okay. Plus my computer's kind of junky, the one I'm on tonight. So if it freezes up, let me know.
While that's going on, if I could interject briefly, those of you who are interested could go to NEXRAD, NEXRAD radar, U of WI, and there's some interesting thunderstorm action taking place in the Midwest right now that the radar will show up.
It's
I'll have you send that out.
NEXTRAD.
I'm gonna have you send that out in the chat. Pamela, you gotta get up in the morning, you gotta take off. All right, thanks for being here. Are we gonna see you next Tuesday? Okay, we'll see you soon, Pam. All
Bob,
right,
can you
Rob,
make
you
me a
ready?
host so I can share?
Yes, sir, stand by.
Sure thing.
All right, here you go, sir.
All right, here we go. So to get onto the NTC website, the best way to do it is to go onto this webpage here. Go down to the training directorate here.
Oh, wait, hold this. How you get to that first page?
So this is just cgaux.org.
Hang on a second. cgaux.org. Okay.
Yep.
And then I get this page here. Okay. Then
hover over the directorates page.
Okay.
And then scroll down to where it says training.
Okay.
Click on that. And then if you go over here on the left side, it'll have this little tab here that says online learning and testing.
Hang on a second, please. Online learning.
Yeah.
And testing. Okay. So click that.
Click on that. And to get into the online classroom, you can click here. Or if you scroll down here, it has these links right here for the online classroom. That'll be where you'll be able to find all the course material that you guys just went over tonight. There's videos and stuff like that. To test out, you're going to want to go right here to the National Testing Center and click on that. And that's going to open up a separate page. You're going to click over here where it says take a test. And it's going to bring up this weird looking thing here. And what we've done now is we removed the need for a second password. So it should work with the same password you use to get on to just about everything else on the AUX page. So you click here. I have my stuff already in, but if you don't have it, it's just your member number and whatever password you use to get into things like AUX Officer. You'll log on there. And then all the tests are here. And you're going to look for, when you're ready to take the test after you finish this course, you are going to look for this one here, which is the WEA course.
Where I don't see it?
Right down here in the way bottom.
Oh, okay. It's black by my thing. The WEA?
Yep.
Okay, I got you.
And you're going to click on that one, and it will bring up this stuff here. This is open book for the moment. I don't know if they're going to go back to closed book. From what I hear, there's no intention of doing that. But there's 50 questions, you get 120 minutes, and you got to get a 90. And to start the test, you just click right here, and then it will bring up all the exam questions. And when it brings up the questions, if you get them wrong and for some reason you don't pass the test, don't freak out. What I always do is I go to review the test questions and look at what you got wrong, and it will guide you back to the places where the answers are so you can review them. That's the easiest way to correct the mistakes if you end up not getting through the first time.
Oh, okay, Rob, I didn't see your one move there that started the test. I didn't see where you clicked it. It's being obscured by the, yeah,
Sure,
I got that part. Go to WEA, I got that. And then the next one, then I click.
Scroll down, and then if you click here, it'll start the test.
Oh, well, I'll figure it out because it's being obscured by the little black boxes on the thing. Okay, thanks, Rob. I appreciate your time. I'll experiment and I'll get right in there. Thank you.
And look, if you guys have trouble, feel free to reach out to me and I will try to guide you as best I can too. So
you want to spell your last name, Rob?
Yeah, what's that?
Your last name.
How do you say it?
Yeah, well, how do you spell it? So in case I get it.
Oh, it's sure. It's gonna be Kilo, Uniform, Mike, Papa, Foxtrot. And if you go on the training directorate website, my contact information is under directorate staff right here. And on the first one on the list, if you click on that. So
okay, thanks, Rob.
If you need help, feel free to reach out. And
thank you. Where are you at?
Guys.
You in Detroit? Where are you? Where are you, Bob? Rob?
I'm over here in the Muskegon area.
Okay, thanks, Rob. I appreciate your time.
You anytime.
Fantastic. Thanks for being here and explaining that, Rob.
Absolutely.
We have our other instructors. Samantha, were there any other questions that came up that we didn't answer right away?
No, the other questions I was able to answer.
Excellent. Chaz, did you have anything you wanted to share? Did you want to, are you there, Chaz? Chaz might have had to go babysit. Let's see, where are you still here, Chaz? Chaz is doing a lot of babysitting lately, so he might.
This particular loaf.
Who's owner? I don't know who that is.
Oh, that's me, Art.
Art, okay, I'm gonna change your name. How do you spell your last name, Art?
Madden, Madden.
Good. Good. So yes, Rob put out information there. At this point, is there any other, because I'll stay to answer general questions about training. Is there any other specific questions that I can answer? So next week, for those of you that got to go or have to get up early in the morning, try to be on time. Don't be late. Make sure you do your reading so you'll be ready, and do the review questions, because honestly, it makes the class go really well. All right, any other questions? Oh, okay, Rob Kumpf just sent out his email. If you have any trouble, you can ask him. Otherwise, and you guys are welcome to go right now. I'm going to stop recording. Thank you all for being here. If you have to